Today we're going to talk about something really useful that we can do once we have an inner product space, and it's called, the topic is called orthonormal sets. Orthonormal sets. Okay, so one problem that we've had to do, one problem that we've had is the problem of getting the coordinate vector, right? So, somebody gives you, so remember coordinate vectors, right? Tell me about the coordinate vector. What is it? Like you have some abstract vector space, you have a basis, B1 through Bn, right? And then somebody gives you a vector in your vector space and says, I would like the coordinate vector. I'd like the coordinate vector with respect to that basis. What is that vector again? Just to remind us. What is that vector? It is a vector of, what information does that vector have in it? Yes?
It's like the coefficients of different basis elements.
Exactly. So what you do is you, it consists of, it is a vector in Rn. It's a vector in Rn where the entries are the numbers that you need to rebuild your vector from the basis elements. Right? It tells you how much of each basis element you need to add together to get your vector. Right? In other words, it's the coefficients for the linear combination that yields your vector. Okay. But sometimes it's not so clear how to get those coordinate vectors, right? Sometimes it's not clear how to get those coefficients, right? I give you a bunch of polynomials, and I say, here's a polynomial, express it as a linear combination of these other polynomials. Well, it takes a bit of work to do it, right? It's not immediately clear. But if we were in Rn, so here's the idea. If we were in Rn, and somebody gave you a vector, suppose somebody gives you a vector in Rn, and they say, I'm not going to tell you what this vector is. I'm not going to tell you what this vector is, but I'd like you to tell me its components. Okay. Well, one way you could pick off the components would be to say, well, I'm going to just take the dot product of this guy against the standard basis. Right? When I take the dot product against E1, what do I get? What's E1? E1 is 1, 0, 0, 0, 0. So when I take the dot product against that, what do I get? I'll pick off the first component. Right? I'm going to pick off, so let's say V is the vector V1, whoops. Suppose V is the vector, V1, V2, Vn. Right? If I take the dot product against E1, then I pick off the first component. Right? If I take it against E2, I'm going to get the second component, etc., etc. Right? So if I don't know the components, right? If I don't know these things, well, I can still use the dot product and figure out what they are. Okay, so this would be a way of figuring out what part, right? And this tells me that V is V1 E1 plus V2 E2 plus Vn En. So this would be a way of picking off the coefficients, right? Okay, so this is what we're going to do in the abstract inner product space. Okay, we hope to do something like this with the abstract inner product space. Okay, so basically we want to create something like the standard basis for an inner product space. Okay, so definition. Again, we are in an abstract inner product space, and we have a bunch of vectors V1 through Vn, and they're all non-zero. All non-zero. none of these guys is the zero vector. Okay. If the inner product of one against the other is 0 whenever I and j are different, we call the set an orthogonal set of vectors. Can I just say an orthogonal set? That's first. Okay, so if everybody is orthogonal to each other, right? Nobody's orthogonal to themselves. If all pairs of different vectors are orthogonal, then we say that it's an orthogonal set. Many of the definitions in this section are kind of obvious. Okay, everybody's orthogonal, we call it an orthogonal set. Okay, so let me just give one example. In the space of continuous functions, you have a space of continuous functions on negative pi pi. Okay, so from negative pi to pi, this interval, you have continuous functions, right? Anybody who's continuous on the interval negative pi pi? We can define an inner product by taking the integral of the product of the two functions. And we actually divide by pi. Don't worry about that 1 over pi. We just do that to make certain things certain sizes. Anyway, don't worry about it. Okay. It turns out, so it's a calculus exercise that we're not going to do. It's a calculus exercise to see that the set 1 cosine x, sine x, cosine 2x, sine 2x, etc., is an orthogonal set. With respect to this inner product. Okay, so this would be a Calc 1 exercise or Calc 2 exercise. Okay, like whenever you take, right, you have to check that cosine x, sine x is equal to 0, right? You'd have to check that any pairs of these guys, and cosine x against cosine 2x turns out to be, they're orthogonal to each other. Okay. So that's an example of an orthogonal set. Okay. Okay. Here's a nice property of orthogonal sets. So I'm going to call it a proposition. Proposition is just like a theorem, but generally not as important as a theorem. It's different from a lemma. Lemma is like some sort of tool that you use to prove theorems, a technical tool usually. Okay, so here it is. If you have an inner product space, and you have an orthogonal set, then the set is linearly independent. The set's going to be linearly independent. So any orthogonal set in an inner product space is going to be linearly independent, right? So remember what we want to show. We want to show that if some linear combination equals the 0 vector, then all the coefficients must be 0. Then all the coefficients must be 0. Okay. And the only thing we have is that these vectors are orthogonal to each other. All the vectors are orthogonal to each other. See if you can prove it. See if you can see why the first coefficient has to be 0, or the second coefficient. All the coefficients will have to be 0. Take a minute and see if you can come up with some reason why. Using the orthogonality of the set. Okay, turn to somebody nearby and just talk with them for a minute, for a few seconds.
That has to do with all of these are switched. All of these, because that's less. So you take and then whichever like vector you're testing, if every other vector is perpendicular or is orthogonal to that, then that would be like S curve. So if it's in the reverse, then it would be S. Like S and S curve.
Okay, okay. Does anybody have something they want to say? Anybody have something they want to say? Right, so we've only got one fact, right? Which is that when you take the inner product of different vectors, you get 0, right? So let's take the inner product, right? Let's use the inner product. We have to use the inner product somehow, right? That's the only property we have. Okay. So what should we take the inner product with? So let's say, well, consider the inner product of this thing against what? Stone? Bj. Okay, I'm going to choose one in particular. just for now, I'll say B1, okay, to make it concrete. Okay. What happens when you do that? What do you get when you do that? What do you get when you take the inner product of this thing against V1? Anybody see it? Russ?
0.
Well, you get some zeros. There's some zeros involved, right? So, right, you've got. Let me pull by linearity. Remember, the inner product is linear, so I can pull this thing out. I get Vi V1 as I goes from 1 to n. Okay. So I is going from 1 to n. When I is 1, I get V1 against V1. That's not 0. Okay. But when I is 2 or 3 or 4 or 5 or whatever, right, up anything other than 1, I get V2 against V1, that's 0. V3 against V1, that's 0. Right? Everybody else is 0. Right? So what happens is that this just turns out to be, you only get, when I equals 1, you get something. You get C1, V1, V1. Right? But when I is 2, you get C2 0 times 0. When I is 3, you get C3 times 0, etc., etc. Right? Okay, so you get C1 times this, times the norm of V1 squared. Okay. So, okay, and actually, Ross was right in the beginning to say that you get 0, right? Because the vector is 0, right? The sum is 0. This is the 0 vector, right? So the 0 vector against this is going to give you 0 the number, right? Right? Okay, so what does that tell you? That tells you that C1 times this thing is 0, right? So that tells you that C1 must be 0, right? Because this is not 0. Okay. Yeah, Nico.
Where did we come up with that? Like, why are we using the summation?
Remember, we're trying to show that these guys are linearly independent, right? That means that whenever you have a linear combination equaling the 0 vector, it must be the trivial linear combination where all the coefficients are 0, right? So this is just, remember, this is just your notation, C1 V1 plus C2 V2 plus Cn Vn.
Okay.
Right? In other words, you want to show if you have a linear combination equaling 0, then all the coefficients are 0. So, I mean, it's just faster to use the summation notation. Okay. Anybody else? Anybody else have questions? Okay. Okay, so we did it for V1, but of course we can change that to, any index. Right? Let's change all these 1s to j's. And so fix a j between 1 and n. Right. Fix some j between 1 and n, and you see that Cj is equal to 0. Right? And that tells you that all the coefficients are 0. Right? Thus, all the Cj are 0. Right? Don't need to say it again. Thus, all the Cj are 0. Okay. Everybody all right? Anybody confused? Anybody confused? No? Okay. So that tells you that any orthogonal set is a linearly independent set, right? And so, any orthogonal set is a basis for its span, right? Because it's linearly independent. Okay. Second remark. If the size of the Vj were all 1, right, for all j, then Cj then the inner product of Ci Vi against Vj would be Cj times 1, right? Cj Vj squared, but that's just Cj. Right? When we took the dot product, when we took the inner product, we got this Cj times the norm squared. But if the norm is 1, we would just get the coefficient off. Right? So that's something nice, right? If everybody has norm 1, then we can pick off the coefficients really easily. We can get the coefficients just like in the standard basis, just like with the standard basis. Okay, so that's why we have another definition. If you have an orthogonal set with the norms of the vectors equal to 1 for all I, then we call this set an orthonormal set. Orthonormal set, right? Orthogonal set with all the norms equal to 1. Okay, this would mean that right, the dot product is going to be 0 if I is not equal to j, and the dot product, the inner product would be 1 if I equals j. It's 0 if I is not equal to j, it's 1 if I is equal to j. For an orthonormal set. I'm always going to abbreviate orthonormal as ON. Okay. So maybe let me write this more succinctly. This equals 0 if I is not equal to j, equals 1 if I equals j. Okay. People actually use something called the Kronecker delta notation. You make up a function called delta sub ij, which is 0 if I is not equal to j, and 1 if I equals j. Because this sort of thing happens a lot in mathematics, so people often use this as an abbreviation for that. So instead of writing this, right, you just write, you write this equals Kronecker, right, delta ij, right? It just means exactly the same thing, right? This is equal to 1 if they're the same, equals 0 if they're different. Okay, we haven't really done too much, right? There's nothing too deep going on here yet. Okay, dumb comment. If you have an orthogonal set, then if you normalize everybody, it's an orthonormal set. Just divide everybody by their norms. Well, then everybody has, all these new guys have norm 1, right? So it's orthonormal. Okay, so going back to our earlier example, 1 cosine, sine, cosine 2x, sine 2x, dot dot dot, whatever. You can stop it. Let's say we stop at some point. Cosine nx, sine nx. So this guy was an orthogonal set, and if you calculate the norms, it's a calculation that if you take cosine kx against cosine kx, you get 1. Or sine kx against sine kx, you also get 1. Sine kx, sine kx equals 1 for whatever k, like for whatever real number, whatever natural number k. Right. So all these guys are norm 1 already. Okay. These guys are all already norm 1. This is why we threw in the 1 over pi. Okay. This is why we threw in the 1 over pi. But when you do the calculation for 1, actually 1 has norm root 2. Right. So to make this an orthonormal set, we need to divide this first guy by root 2. So, right, this guy isn't norm 1, we divide it by his norm, then he becomes norm 1, we get an orthonormal set.
Is that 2 supposed to be root 2?
No, because this is the square of the magnitude. Right? So the magnitude is the square root of that.
Right.
The dumb comment leads to a boring definition that a basis that is orthonormal is called an orthonormal basis. Like I said, most of the definitions are kind of obvious in this chapter, in this section. Okay, orthonormal basis. This is actually what we were hoping for. Boring as the definition is. Let's see. Useful properties of orthonormal bases. So first off is something that we've already noticed, that if U1 through UN is an orthonormal basis for an inner product space V, if you have some arbitrary vector that's a linear combination of the UI, then the coefficients are just what? Coefficients are just the inner product of the vector against the element, right? You just take V against UI, right? As we just saw, like 2 minutes ago. Okay, so for example, if we know that a function is some combination of cosines. Right? Suppose you know that your function is some combination, some linear combination of cosines, right? Of cosine waves. Okay. Well then, we can figure out the coefficients, right? The coefficients are just going to be the inner product of your function against the appropriate cosine. Right? If you have some machine that can take inner products, right? That can integrate, you have some machine that can integrate your function against a cosine wave. Okay, and it will give you some number. Well, that number is how much of that cosine is in your, how much of that wave is in your function. In some sense, every function that's continuous on negative pi pi actually is a combination of the form a naught times the constant plus summation ak cosine kx plus summation bk sine kx. Okay, so if you have any function on negative pi pi, there's a way of expressing it as a linear combination of sines and cosines, okay, and the constant function. Okay, and so if you want to figure out what combination it is, you just use the inner product, right? Right? To figure out, to determine the coefficients, just take the inner product of f against whoever. Right? If you're trying to figure out, a5, do it against cosine 5x. You're trying to figure out b3, take the inner product of your function against sine 3x. Okay, and that'll tell you what coefficients you need to build your function back up. Okay, this is the idea of what's called Fourier analysis, or more precisely, Fourier series. Okay. An idea that was proposed in the late 18th century, I think 1798 or something like that, by a man named Fourier. It was such an outlandish idea that nobody believed it at the beginning, right? Is it true that any function can be broken up into combinations of sines and cosines? Right? Does that seem plausible? It didn't to most everybody at that time, right? Everybody said, you're crazy, that's impossible, it's not true. Okay. But this is actually how sound is digitized, right? How do you take a sound, me talking to you, and then turn it into something that can be stored digitally? Right? How do you take music and store it digitally? Well, you break it up into little pieces, and then you say, I'm going to take that piece and express it as a bunch of coefficients. I'm going to express it as a bunch of sines and cosine waves. And then you say, how much of each wave? right? And you pick off those coefficients. You don't have to pick off infinitely many coefficients because humans can't hear, past a certain point, right? As k increases, your frequency is increasing, right? So you don't have to pick. You don't have to go to infinity. You can stop at some point, right? So, right, and then you store those coefficients on your CD if you're old, right? Or in your whatever you have now, right? Anyway, so in your phone, I guess, right? So then the phone will say, well, how do I reconstruct my sound? I've got all these coefficients. That tells me what sines and cosines I need to put back together to get my original music. Okay. So this is how that works. And that's not really true, right? They don't use Fourier series anymore. But this is the first idea in that direction. Now you use something more complicated. I think you could use something called wavelets. Wavelets. It's little waves as opposed to these infinite waves of right, because the sine and cosine go on infinitely in all directions. Yeah, the first time, when I first gave this example years ago, people were like, "Oh yeah, okay." But then after a while, I think it was I gave this example and somebody said, "Excuse me, Professor, we don't use CD players." Like, oh, okay, yeah, yeah, okay, 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 okay. So where are we? Okay, let's go back here. Okay, so we have the theorem that we already proved, right? That you can pick, if you have an orthonormal basis, you can pick off the coefficients. Orthonormal basis, you can pick off the coefficients. Okay. There are some corollaries of this. Corollary. Let's say that V is an inner product space, and again, U1 through UN is an orthonormal basis. And an orthonormal basis. Suppose you have one vector that's summation AI UI, and you have some other vector that's summation BI UI. Okay. Then what happens when we take the inner product of one against the other? What happens when you take the inner product of this one vector against the other vector? I'll let you think about it for a minute, see if somebody can come up with the answer. Okay, turn to somebody nearby, see if you can say something. Okay, should I give 1 point on the final to whoever has the right answer? Molly.
Is it just the summation from 1 to n of ai, bi?
Yes, it is. Great. Right, so you say, okay, look, I can pull out the the sums and the scalar multiples. Right. Lizzie, do I owe you a point too? Did you have it?
Yeah.
You have it? Okay. Okay, good. I'll give you.
Yeah,
And the- okay, good. I should just award you guys points automatically. Okay. Okay, so right, so you see what happens, right? This is going to be 0. ui against uj is going to be 0, except when I and j are equal, right? I and j are both ranging, right? I ranges from 1 to n, j ranges from 1 to n, right? So I sticks at 1, right? I starts at 1, j goes from 1 to n, I goes to 2, j goes from 1 to n, I goes to 3, j goes from 1 to n. But most of those terms are 0, except when I and j are equal, right? So when I is 1 and j is 1, you get something, but everything from j equals 2 onwards, you get nothing, right? And so what you get is just the sum I equals 1 to n, ai bi times ui, right? Those are the only things that survive, right? And so you get, because this is 1, which is orthonormal, you get ai bi. In other words, the dot product of the coefficient vectors, right? You get the dot product of the coefficient vectors, right? This thing, if we look at its coordinate vector, with respect to this basis, it's right a1 through an, and the other one is b1 through bn, right? What you see is that this is right, the dot product of the coordinate vector against the other coordinate vector. Okay, so that's cool. Right, so you have this sort of, again, sort of a mirror world, right? You've got V, you've got inner product in V, right? This thing corresponds to its coordinate vector. This thing corresponds to its coordinate vector. And these guys, the coordinate vectors lie in Rn. In Rn, we have the dot product, right? U of B dotted against V of B, right? So these things actually are equal, right? These are corresponding, right? But these numbers are actually equal to each other. The last thing we were going to mention is a corollary of the corollary called Parseval's formula. Namely that if you have a vector, so same setting, right? You've got V in inner product space, you've got B an orthonormal basis. If V equals summation Ci ui, then the norm of V equals what? By the previous thing, you can take U against U, what do you get? No, not 1. U against U. I'm saying V against V. I'm sorry, U against U is 1. Sorry, V against V. Right? To get this, you need to take the V against V square root. Right? So what do you get? What do you get? Right? V is summation Ci Ui. Right? So you take the dot. You're going to take. Somebody say it, please. Thank you, Russ. Ci, what? Summation Ci squared. Right? Everything to the 1/2. Right? Summation Ci squared, everything to the 1/2. In other words, right, is that okay? Right? You got, right, just from the previous thing, right? You get the dot product of the coefficients. You get the dot product of the coordinate vectors against each other. Right? The coordinate vector is C1 through Cn, so you're going to get, the dot product of C1 through Cn against itself. That's just summation Ci squared. Right? We got the half here. Right, but you see what that is, right? That is actually the, so you take the coordinate vector and you take its little L2 norm. Right? That's the little L2 norm of the coordinate vector. That's just by definition. Right? Remember, little L2 norm means you square you take the sum of the squares and then take that thing to the square root. Okay, let's stop there. Let's stop there for today. We'll finish up this section next time and go on to the last section of this chapter.